All right, so what I have here is sine x. Sine x doesn't look anything like 1 over 1 minus x. And that's an important formula for a power series because the sum of x to the n is the function 1 over 1 minus x. Well, if a function doesn't necessarily look like 1 over 1 minus x, then what are we able to do? We just learned, we just talked about it. Okay, tan inverse of x doesn't look anything like 1 over 1 minus x. But we still found a power series. Natural log of x doesn't look anything like 1 over 1 minus x, but we still found a power series. So how did we find power series or power series representations of functions if the function didn't look like 1 over 1 minus x? What did we do?
You take the derivative or integrate?
Yeah, you took the derivative or you took the integral and you hoped to see something that looked like 1 over 1 minus x, and then you went from there. And now we're going to look at other functions like sine x. So let's think about sine x for a minute. Sine x doesn't look anything like 1 over 1 minus x. But maybe its derivatives or integrals do. But notice that the derivative and integral of sine x is just cosine x, and that's even worse. That doesn't look like 1 over 1 minus x. So how could we come up with what we call a Taylor polynomial that would approximate this function? Well, what I'm going to do here is I'm just going to demonstrate by showing you a couple of things here that there is a polynomial that I could create that's going to be centered at 0, okay? To where if I were to increase the power of the polynomial, it would start to fit the curve a little bit better. So let's first of all recognize that the function value itself should match the value of the function. So that is just a constant polynomial, in this case, when the polynomial was an nth degree polynomial of 0. But now let's make that 1. And so if I were to zoom in on that now, you should start to realize, wow, not only does the function value equal that curve, but so does its derivative. So does the tangent line. So I basically created this tangent line approximation here, which is y equals x in this case, in order to approximate the curve. But now let's make it n equals 2. Wait a second. Does that look like a polynomial, like a quadratic? Right. I'm approximating it with a quadratic polynomial where n is equal to 2. It's an nth degree polynomial. So what do you think that means that this still looks like a line? Okay, so I'm starting to see that sine of x is starting to look like, well, 0
X
plus x plus something. But it doesn't look like, hopefully you're noticing, that's not quadratic. So what does that imply?
that is just x to the power of 1.
That it's x to the power of 1, but it's supposed to be a quadratic approximation. N is equal to 2. So what would that imply about my coefficient of x squared?
It's
Not
0.
big enough.
That there isn't one there. So obviously that all that means is that we're not using a quadratic approximation. Okay. By the way, well, I'll tell you that in a minute. So then if n is equal to 3, now notice, okay, so now we have a cubic polynomial. Great. What is the cubic polynomial? Well, I don't know. That's what we're going to be learning how to create today. But you can see now that if you go back to n equals 1, look at how from our perspective, it stopped actually curving along. It stopped actually following the curve right around here somewhere, right? And then if I made that n equals 3, look at how it seemed to mold to the curve a little bit further. And now let's make n equal 4. Oh, wait, n equals 3 and n equals 4, those looked pretty much the same. Okay, so n equals 3 and n equals 4 looked the same. Why do you think n equals 3 and n equals 4 look the same?
Fourth polynomial, or the fourth term is 0.
Yeah, it must mean that the fourth term has, see, so it tells me that there is some sort of x cubed term. I don't know what it is. We'll call it c. But there is no x to the fourth term. And it looks like there's an x to the fifth term. Oh, look at that. It molded a little bit more. No x to the sixth term, but there is an x to the seventh. Molded a little bit further. No x to the eighth, but there is an x to the ninth. Molded a little further. There is no x to the 10th, but there is an x to the 11th. And so notice that if I were to continue this infinitely, okay, then that
Professor,
finally
you
molds
cut out.
to the curve.
Professor, you
So
cut
let's
out.
just play that again and recognize that you've got a linear. Oh, I was cutting out. I'm sorry about that.
We lost about the last 30 seconds of what you were
Oh,
saying.
really? Yeah, sorry about that. Okay. I had some issue with my internet. That's weird. What I was saying is that essentially you could just continue to, if I were to start this at n equals 0, that we could just play this and recognize that as the number of terms in my expansion increase, notice how it continues to mold to that curve further and further and further away from 0 until I get to n equals 9, and then I get to n equals 11, and I could see that eventually, if I were to add an infinite number of terms, I would end up creating the curve for sine of x. So I could approximate sine of x with an nth degree polynomial, which we refer to as a Taylor polynomial, otherwise known as a Taylor series. Okay, so why don't we go ahead and change this now by changing the starting point. Let's say that we were to center this instead. Let's say we centered this at 3, okay, or 4. If we were to center this somewhere else, now notice that the only difference here is that the centering point changed. But if I were to continue to increase this, notice that there would be a tangent line approximation at that point. There would be a cubic approximation. There would be a x to the 5th approximation, an x to the 7th approximation, x to the 9th, x to the 11th. They would be different polynomials because I would be centering at a different location. So what I'd like to do here is just take a look at this x to the 11th approximation. And I'd like to just play this by showing you what happens to this as I start moving. Let me slow this down a little bit. Look at how it just seems to kind of be, as it says here, just seems to be kind of crawling across the curve, right? So all I'm doing here, let's slow this down, and let's change this from -10 to 10. Okay, and play that again. Okay, so as it seems to be just move, as my point is centered at this particular location, I'm spreading out the distance in both directions, and all that's happening is I'm getting brand new polynomials, okay, brand new polynomials depending on what location I'm at. Every one of these is considered a Taylor polynomial. In this case, it's a degree 11 Taylor polynomial. Now let's center it at 0. And what we've just created is a Maclaurin polynomial, a Mclaren series. So those are just two names for the people that discovered this. And our job then is to try to figure out how could I start with a function and create a Taylor polynomial for that polynomial. Now, the most important part of a Taylor series is that in order for this particular polynomial to equal sine of x, then I know that the function value of sine x has to equal my polynomial. But every single derivative better also equal that polynomial. So the derivative of every of that polynomial should equal every derivative of sine x. So the first derivative of sine x should equal the first derivative of the polynomial. The second derivative of sine x should equal the second derivative of the polynomial. The fifth derivative of sine x should equal the fifth derivative of the polynomial. And so that's what we're basically doing to build this Taylor polynomial, is that we're going to say that if we take better and better and better approximations, that every single one of its derivatives better equal that function. Okay, let's just take a look at cosine x is real similar. Let's just take a look at e to the x. Okay, and now let's change this to 0. Okay, so the first one here, n equals 0, is 1 in this case. And if I were to increase this to 1, now all of a sudden notice how its derivative is equal. So the derivative has to equal. Now we're going to see that its second derivative has to equal, and its third derivative, and its fourth derivative, and fifth, and sixth, and seventh. And so notice that as we go out to the 11th degree polynomial, look how closely on the left side this seems to be molding to it, and how quickly it molded to it, right? If I went back to 3, 5, 7, or 5, 6, 7, 8, 9, 10, 11, notice how the right side is already getting to where it needs to be, while the left side is just taking a little longer because it's not actually ever going to approach an asymptote. But if we have enough terms, notice that, notice that if we were to go back again, just focus on the left side when I increase. Notice that increasing just seems to be spreading that left side a little bit further down that place that's getting close to the asymptote. Cool. Now if we were to make this 30, okay, let's just keep going. Watch that left side. Oh, maybe that didn't work. Hold on. Oh, that's because the program only went to number to 11. The program only went to 11, so that's why they stopped at 11. So anyhow. All right, so we all good there? Okay, so let's go ahead and take a look at this then. So we're going to start off by approximating this polynomial. So 2x to the 5th. Okay, let's go to okay, so this is kind of a funky looking polynomial, right? It doesn't look too interesting until you kind of slide right in here and you see this little concavity change happening right in this location. Zoom in a little more and it starts to just look like a line, right? And so what we're going to basically try to do is we're going to try to create a Taylor polynomial for this polynomial. Now it might seem like, well, that's kind of stupid because it's going to equal itself. I mean, the Taylor polynomial for this polynomial will be that polynomial. But the reason why we're going to do this is because it'll give us an understanding of what we're essentially trying to do here. Okay. So let's go to our example here. Okay. And let's start with that polynomial. Okay. So given this polynomial, 2x to the 5th plus 3x to the 4th plus 6x plus 1, we're going to reconstruct, it's not an n, it's a quotation mark. So reconstruct this polynomial term by term. By finding the Taylor polynomial. Okay. Which would look like just an x to the 5th polynomial with every single term. So if I just have a 5x to the 5th plus a 4x to the 4th plus a 3x cubed, and so on, then basically what I'm going to do is term by term, I'm going to find what is the constant term, and then what is the linear term, and then what is the quadratic term, and then what's the cubic term, and so on. So what we're going to basically do here is just start from scratch, and we're going to recognize that as I take each of these derivatives, then I should be able to find what each of the coefficients are going to be for that expanded polynomial. So I'm just going to start with the simple way here to do this. And let's just say, let's find f of 0. Okay. Well, look at f of 0. F of 0, that's pretty simple. It's just 1. Right? So f of 0 equals 1. But in order to build the Taylor polynomial, we said that all of the derivatives should equal as well. So let's find the derivative then. So what's f prime of 0? Okay. Well, before we find f prime of 0, we should find the derivative at x and then just plug in 0. So let's find f prime of x, and that's just 10x to the 4th plus 12x to the 3rd plus 6. Cool. Okay, but if I want to then find f prime of 0, then that would mean that if I'm going to build this new function, that this would have to have a derivative of 6. So not only would I have to make sure that my function is going through y equals 1, but I should also make sure that as it's going through y equals 1, it has a slope of 6. But then I have to find the second derivative as well, okay? Because I need to make sure that my curve matches the same second derivative. So f double prime of x would have to equal 40x to the 3rd plus 36x squared. And that implies that my second derivative at 0 should equal 0. So that means that I won't have a second derivative, or my second derivative would be 0, which means that I have a concavity at 0, a point of inflection. So that would mean that if I were to rebuild or build this function that's going to approximate this function, my y value should be 1, my slope should be 6, and I should have a point of inflection at 0. But notice that that's pretty much, the second derivative is the last kind of aspect of a graph that we really understand, that it's physical interpretation. So from this point on, we're just going to make sure that each of the subsequent derivatives are going to match numerically. So this is 120 x squared plus 72x. Okay, well that must imply that my third derivative, or my third derivative at 0, is also going to be 0. Okay, well that was an interesting again. Let's go ahead and continue. So if we take the fourth derivative, now notice from this point on, we're just going to use the notation for higher order derivatives by putting that in parentheses. This gives us 240x plus 72. Okay, well that's nice, because now if I look at the fourth derivative at 0, the fourth derivative at 0 is going to give me 72. So that means that for my new function, my approximation, I better have the same exact function value, first derivative, second derivative, third derivative, fourth derivative. Let's see if we can continue. Okay, fifth derivative. Let's look at the fifth derivative. So the fifth derivative at x is equal to 240. And so we just need to notice that our fifth derivative at 0 is equal to 240. Okay. Well, what does that mean? Okay. Well, all I've done here is I've done all the work to find all of the different derivatives that are going to be important here. Okay. So now let's go ahead and go back to our standard polynomial. Okay. We're trying to rebuild this polynomial here. So that must mean that the function value should equal the same as the function value at 0 here. So if I were to just start off by looking at p of 0, notice that p of 0 should equal, well, a0, because everything else canceled. So that must mean that automatically I can tell that my constant term is going to be 1 because of the fact that I've now shown that a0 is in fact equal to 1. And I've already rebuilt my first starting point, 1. Okay, well, if I go back to Desmos, that's an approximation. Y equals 1. Well, I mean, it's a good approximation, I guess, but it's only going to tell me where I am at this location. So I want to approximate it maybe with a linear polynomial. So that's why we're going to go ahead and start to take some derivatives. So let's find p prime then. Okay, well, when I find p prime, notice that all I'm doing is bringing the power to the front and reducing the power by 1, right? So this gives us 5a5 x to the 4th plus 4a4 x to the 3rd plus 3a3 x squared plus 2a2 x plus a1. All right, so anybody see anything interesting that happened when I took the derivative before I find what p prime of 0 is? Anybody see anything interesting about this? Anything?
A0 is gone now in the derivative.
A0 is gone. Good. And A0 is gone because I didn't need it anymore because I already found what it was. Constants disappeared. So thank you. That's one thing. Anything else?
A1 is 6.
A1, well, before we get there, we're going to see in a second what A1 is. But we will see that A1 is 6 because aren't all of the x terms when I plug in 0 going to cancel out? So now I've got a new constant because it was the old coefficient of x. So that must mean that p prime of 0 is just a1. Right? P prime of 0 is a1. And that must imply that if the derivative is supposed to be the same as the derivative of the function, then that must mean that a1 is equal to 6. Great, which now means that I can go back here and I can create a new function. Not y equals 1, but y equals 6x plus 1. Okay? And now notice that that matches the slope. But if I start to move away from that, I'm eventually going to see that it's not actually going to be accurate because I could see now that there's a little bit of a gap now between. So maybe I could add some more terms. Okay, so that's why we're now going to go to the next one. And we've got p prime of or p double prime of x is equal to, well, now I'm going to multiply 5 times 4, but I'm not going to say 20. I'm going to say 5 times 4. So I'm going to say 5 times 4 times a5 times x to the third plus. Now let's move the 3 to the front. We get 4 times 3 times a4.
Why are we doing that instead of multiplying it out?
Patience.
Kind of pattern.
Patience, Abby. Okay. No, we're just doing this so that we can see what this pattern is going to be in a second. So we could multiply it out, but if I just wrote 20 and 12 and 6, I wouldn't really see exactly where those numbers are coming from. So what we're going to do instead is we're just going to write out the coefficients we see here. Okay.
Professor,
Yes.
I noticed something a minute ago when we were taking the derivatives of the f function. I was just wondering if I was onto something. I was just looking at that, and I don't know if this is just doing the same process backwards or if it's actually useful, but when we got down to some of the lower powers, I just divided the coefficients by the factorial of the order of the derivative and ended up coming back with the original coefficients of the f of x function. I was wondering if that could be used for this type of problem.
Well, that's essentially, Sean, what we're about to notice. And you might start noticing a couple of those happening right here. Like, look at the coefficient of this term. It's 2 times 1. That's 2 factorial. Look at the coefficient here, 3 times 2 times 1. That's 3 factorial. Look at the coefficient here, 4 times 3. Okay, well, that's not quite a factorial yet, but it looks like it's starting to become factorials, right? So what I'd like you to realize then is that technically, when I ended up going back up here, this was also technically 1 times a1, because I moved the power of 1 to the front to get 1 times a1. And so when I now go back again and I just find p double prime of 0, notice that I get that this is 2 factorial times a1. That should be a2, shouldn't it? This should be a2 over here. Okay. And so notice that a2 is not automatically 0. 2 factorial times a2 is equal to 0, which means that a2 is equal to 0. Okay. So we get that. Which should make sense, because if you look back to our original polynomial, we don't see a quadratic term. So now let's just keep going. Let's find a couple more derivatives. We're just about done here. We find another derivative, the third derivative here. Notice what happens now again. Because of the power rule, isn't that 3 going to multiply to what's already here? Which now ends up giving me 5 times 4 times 3. 5 times 4 times 3, a5. And now I reduce that power. Now over here, I get 4 times 3 times 2, a4. And that reduces it to x power. And now over here, this power is 1. So this becomes plus 3 times 2 times 1 times a3. So this coefficient is 1 factorial. This coefficient is 2 factorial. This coefficient is 3 factorial. So notice that if we find the third derivative at 0, if we find the third derivative here, then all that's left is 3 factorial times a3. So I hope that what you're recognizing here is that in order to find each of these particular values, all I'm doing is recognizing that the unknown quantities are a factorial multiplier of whatever the actual value is. So that must mean that if 3 factorial times A3 is equal to 0, then that must also imply that A3 equals 0. A3 equals 0. Which makes sense because I have no cubic term either. So that just means that I have 1 as my linear or my constant term, 6x as my linear term, no x squared, no x cubed, but apparently I'm going to get 3 for my next answer somehow. And the way that I'm going to get my 4th degree polynomial is by looking at my 4th derivative. To get my 5th degree polynomial, I'm going to look at my 5th derivative. So the more terms you get, you're just looking at one more derivative. So we got 2 more derivatives to take care of here. So let's find the 4th derivative then. The 4th derivative of p. Well, by the power rule again, we get 5 times 4 times 3, but now that exponent of 2 moves to the front, which continues to get me more powers, a5x plus, and now we're left with 4 times 3 times 2 times 1, a4 x to the 4th, or is just a4. And we should recognize at that point that the coefficient of a4 is sure enough also 4 factorial. There's a really cool pattern happening here, which really means again that the 4th derivative at 0 is equal to 4 factorial times a4. All right, so this is where I'm going to take a side note now. My actual 4th derivative at 0 was 72. The value that I'm trying to find is a4. So what that implies is that I could say that 4 factorial times a4 is equal to 72. So if the 4th derivative is 72, then that must mean that a4
equals 3.
Equals 72 divided by 4 factorial. But what is 72? 72 is nothing more than just the 4th derivative at 0. 4 factorial is the factorial that matches the derivative. So 72 divided by 24 gives me 3. So notice that 3 is my 4th coefficient. That corresponds with what we expected in my original. My 4th degree term better have a coefficient of 3, which now means that if I go back to my polynomial and throw in a 3x to the 4th here, now I should be able to zoom out and realize, man, that should look really close to what it's supposed to be when I look at 0. Okay. But notice that you can see up here that as I zoom out, first of all, it's pointing the wrong direction. Secondly, if you go over here, it's not actually following the red line, right? But that's because it's not a perfect approximation of this polynomial yet. So now let's go back again and let's do our last step. Our last step is to find the 5th degree term. So the 5th derivative of x. Well, notice the only term that's left is this one right here, because this is going to go to 0. So all that's left is that the 5th derivative is 5 times 4 times 3 times 2 times 1 times a5, which implies that the fifth derivative at 0 is equal to 5 factorial times a5. Well, that's important because I know that my fifth derivative at 0 is supposed to be 240, but I also know that my fifth derivative of my Taylor polynomial is 5 factorial times the unknown constant. So that must mean that if I were to go through this process yet again, then I know that 5 factorial times my unknown constant is equal to 240. So that means that my last unknown coefficient is 240 divided by 5 factorial, which means, hold on, if I want to now find that fifth coefficient, I just need to know what's the fifth derivative of the function at 0 divided by 5 factorial. 5 factorial is 120. This gives me 2, so that must mean that 2 is a5. Now this might not seem like too surprising or exciting until you realize what the hell we just figured out. What we just determined here is that if I didn't want to go through all of this process and all I needed to find were the coefficients of each of my particular polynomial terms, all I need to know are what are the first few derivatives, and I divide those derivatives by each of the subsequent factorials. So if I were to now look down below, that's why the degree 5 term, the degree 5 coefficient of a5, had a coefficient of the fifth derivative divided by 5 factorial. And this is the crux of creating a Taylor polynomial. If I want to create a Taylor series, okay, so a Taylor series centered at A will essentially just be a function, more specifically a polynomial function, that looks like f of A plus, well, then you would end up having an x minus A term, but bear with me. Then you would have an x minus A squared term. Then you would have an x minus A cubed term, and so on. But notice what we have just learned right up here is that the coefficient of each of these terms is nothing more than just the derivative of the function at A divided by 1 factorial, which means the next one is the second derivative evaluated at A divided by 2 factorial. And the next coefficient would be the third derivative evaluated at A divided by 3 factorial. And so this process of creating a Taylor polynomial, and likewise, you could even see that this is just f of A over 0 factorial, is that now the Taylor series is nothing more than just the sum from n equals 0 to infinity of the nth derivative at A divided by n factorial times x minus A to the power of n. So this is what we refer to as a Taylor series, but I just want to focus more on a Maclaurin series because this is the one that we use most often. And a Maclaurin series just replaces all of those x minus a's with just x. So if I were to look at a Maclaurin series now, this is just a Taylor series centered at 0. Okay, so in this circumstance, we get f of x equals, well, we're still going to get the leading term of f of 0, f of a, but now it's going to be f of 0 plus, and now the next term is just going to be an x term. The next term is just going to be an x squared term, because notice that x minus 0 is just x. The next term is an x cubed term, and so on. What changes from term to term are the coefficients. So this is nothing more than just the derivative at 0 divided by 1 factorial, which is just 1, plus the second derivative at 0 divided by 2 factorial, plus the third derivative at 0 divided by 3 factorial, and so on. This is really cool because now what we're showing is that the polynomial is related to the function simply by making every single one of that function's derivatives equal. So equal to what the original function's derivatives are. So what we want to do is just get some practice now by revisiting this Desmos activity with sine x. So remember how we ended up coming up with sine x over here? Okay, so we had sine of x, and notice that we ended up creating some different polynomials, and we would like to come up with how these polynomials came about. Okay. So here's the idea. Okay. Now we're just going to do some examples here. I'm going to start off with sine x, and then I'm going to ask you guys to do a couple of other functions. So essentially all we're doing here, oh, and I guess I should probably go back up here and just reiterate what this is. So notice that this Taylor polynomial is just equal to the sum from n equals 0 to infinity. All I'm going to have is going to be x to the power of n. It's just that every coefficient is going to be the nth derivative at 0 divided by the corresponding n factorial. Okay, so look at how basically what we're showing here. Every single function, any function, sine x, cosine x, natural log of x, e to the x, whatever function you come up with, has a power series representation. And all they are, if you were to center it at 0, is x to the n times this special coefficient. So that special coefficient is going to be our c sub n pattern, okay? And that's what's going to make one series different from another series, okay? Everybody cool with that? So yeah, Eric, I'm showing the OneNote, so there might be some issue with your connection if you're not seeing that right now. Okay. All right. All right, so let's go ahead and do that for sine x. So we want a power series representation of sine x. So find the Maclaurin series for f of x equals sine x. Now I don't have to stipulate centered at 0 because that is what the Maclaurin series is, okay? All right, so let's go through the things that we need. I mean, if you look at this Taylor series, what are some things that I'm definitely going to need?
A bunch of derivatives.
A bunch of derivatives. So let's just start to find some derivatives. So I like to just create a list. Let's start with f of x equals sine x, and let's just start taking a bunch of derivatives. So that would mean that f prime of x is equal to cosine x. That would mean that the second derivative is negative sine x. The third derivative is negative cosine x. The fourth derivative is sine x. Now, the reason I'm going to stop there is because you should notice that all derivatives are going to repeat themselves from that point on. Okay? And this is just a good kind of rule of thumb. Go to 4 derivatives, and that should be able to take you to at least a fourth degree polynomial. Okay? So what else am I going to need in order to find the Taylor series polynomial?
Plug in 0 for those functions.
Yeah, so we're going to have to find out what is f prime of 0 and f double prime of 0 and f triple prime of 0 and so on, right? All right, so that means that we should find each of these derivatives at 0. So we find f of 0, okay, and we need f prime of 0 and so on. Now, before we do this, I'd like to revisit that Desmos graph. Remember how we said that there was a linear approximation? It was right there. But there was no quadratic approximation? There wasn't a quadratic approximation because the coefficient will turn out to be 0. But then we did see a cubic. But then there was no quartic approximation. But then we saw a quintic. But there was no degree 6 representation. And so it looks like the sign expansion will only have the odd powered terms. That's what it kind of appears to be in this situation here. Well, let's see why. What is sine of 0?
0.
So doesn't that mean that this is 0 then? But then cosine of 0 is 1. Now we're back to negative sine of 0, which is 0. But negative cosine of 0 will be negative 1. And then sine of x will be 0. Okay? And so what we're recognizing here is that the first degree term will have a coefficient, but the second degree term will not. The third degree term will have a coefficient. The fourth degree term will not. This is demonstrating why, if we look at it just on the graph, it appears that there is no quadratic approximation, no quartic approximation. That's because the only terms that we have are these particular values of the odd degrees.
Is it just a coincidence that that pattern happens to be the values of sine x from 0 to 4?
Yes, total coincidence. Okay, so that's I mean, I hate to say that that's a coincidence. It is interesting to say the least, but I would say that it is coincidental simply because of the fact that the only reasons we got negative 1 and 1 were from cosine functions, not from sine functions. Okay, so we're now ready to come up with the approximation for f of x equals sine x. But sine x apparently has no constant term, right? So I'm going to continue to write these. Okay. So I'm going to say that it has no constant term. Okay, so it's just 0 plus, but it does have a linear term. It's 1 over 1 factorial times x. But it doesn't have a quadratic term. It's 0 over 2 factorial times x squared. But it does have a cubic term, it's -1 over 3 factorial x cubed. But it doesn't have a quartic term. But it does have a quintic term, 1 over 5 factorial x to the 5th. But it doesn't have an x to the 6th term. So what we've done here is we have just come up with the pattern for what sine x is going to look like. Sine x will simply be x minus 1/6 x cubed plus 1 over 120 x to the 5th minus 1 over 720, no, not 720, 5040, x to the 7th, plus, and so on. So we should recognize a few things. That sine x can be approximated with a polynomial with only odd powers. We can see that it is an alternating series because it switches from positive to negative to positive to negative. And the coefficients of each of those terms were directly related not only to the derivatives at each of those values, but also to their corresponding factorials. And so if we were to graph this term by term, we would start to recognize that this turns out to be the approximation for sine of x. That's pretty damn cool. But we're actually not quite done, because now let's come up with the actual power series. Okay, well, let's think about how we end up getting each of these terms, right? So this right here is our A0 term, and this is our A1, and this is our A2, and this is our A3. And so let's just start with the x component, okay? X to a power. Let's think about this. I plug in 0 and I get an answer of 1. I plug in 1, I get an answer of 3. I plug in 2, I get an answer of 5. Can anybody think of what the power would be for that?
2n plus 1.
Yeah, 2n would make it go up by 2, but plus 1 would make it a power that's odd. So any odd power would be 2n plus 1. Now let's focus on the alternating signs. Well, this is first of all going to have a coefficient that is alternating. So I know that this is going to be -1 to the n, because when I plug in 0, I get positive, and it'll alternate from there. And now I've got to realize that this right here is just going to give me 1 factorial, 3 factorial, 5 factorial, 7 factorial. So notice that the denominator is going to match the power. So that must mean that over here, the denominator is 2n plus 1. And we have just created the power series representation for sine x.
Factorial, right? 2n plus 1.
Factorial. Yes, thank you. That's a factorial.
Can you repeat the last part? How did you get 2n plus 1 factorial?
Well, that's because if you take a look at each of these denominators, 5040 is 7 factorial. 120 is 5 factorial. 6 is 3 factorial. Notice that that factorial matches the power. And that factorial of 5 factorial matches the power of 5. That factorial of 7 factorial matches the power of 7. So since I got 2n plus 1 as my power, then I know the denominator is that same number factorial. Okay?
Yeah, that makes sense. Thank you.
And there you go. So now what we've done here is we've created a power series that looks nothing like 1 over 1 minus x by simply recognizing that we could use derivatives and factorials to come up with those coefficients. I hope that's pretty damn cool. But But again, for cosine x, you just take it a few derivatives, okay? And when you take a few derivatives, you notice that every other one is going to be cosine x. And obviously, when I plug in cosine of 0, that's when I'm going to get 1s and -1s. Now, similar to what happened with sine x, except for notice that the first derivative and third derivative terms gave me answers, but there were no constant x squared x to the fourth terms. That's going to be the exact opposite for cosine x, because now, if we follow this pattern, the first term is 1. Second term is 0 over 1 factorial times x. Third term is -1 over 2 factorial x squared. Next one is 0 over 3 factorial x cubed. Next one is 1 over 4 factorial x to the fourth. And so we should realize with cosine that we actually do have all of the even powers now. Sine of x gave me all the odd powers. So we could still see that they're alternating signs. So that gives me -1 to the power of n. But each of these denominators as well are still matching the numerator, or the exponent. So this is an exponent of 2, and the denominator is 2 factorial. This is an exponent of 6, and the denominator is 6 factorial. So now you should be able to recognize that the factorial on the denominator is going to be exactly the same as what the exponent is. And since all of these exponents are even powers, that gives me an exponent of x to the 2n. So again, this is the power series representation for this function cosine x. So cosine x, if you were to add an infinite amount of polynomial terms, would eventually become this polynomial.
Professor?
Yeah.
So I got the same thing, but for my alternating series, I got -1 to the n-2.
That's fine. It would still be n-2 or n is the same thing. Because if you think about, let's say n was 5. If I subtract 2, now I get 3. -1 to an odd power, whether it's a 3 or a 5, is still going to be the same thing. Right? So notice that n and n-2 are technically the same when they're powers of -1. Make sense?
But if you plug in 2 for your alternating series, wouldn't that mean that...
Well, let's try it. If I plug
Wait,
in
hold on.
2,
Oh, never mind, I'm sorry.
squared is 1, so that would just give me a coefficient of positive over 4 factorial x to the power of 4. Everybody cool with that? All right, so let's look at sine x real quick. Sine of x was an alternating series, and it only had the odd powers. Now I look at cosine x, also an alternating series, but it only has the even powers. Now let's look at e to the x. E to the x should have been a pretty simple one, because you realize that e to the x is its own derivative. So every single derivative is e to the x, and therefore e to the 0 for every term will be 1. So I'm not missing any terms this time, because the only way I miss terms is when the derivative turned out to be 0. But all of these give me 1. So notice that if I wanted to write the expansion, then that just means I get 1 over 0 factorial x to the 0. I wrote that for a reason, because this is why the leading coefficient is always going to be whatever f of 0 is. Because x to the 0 is 1, 0 factorial is 1. So all I'm going to be left with is the function value at 0. So this is just 1. 1 over 1 factorial x to the first, 1 over 2 factorial x squared, 1 over 3 factorial x to the fourth. So notice that this does not miss any terms. This actually has all of the terms involved. So e to the x is nothing more than just a sum. It's not an alternating series this time. E to the x is just a sum of multiple terms where the power matches the factorial in the denominator. And so e to the x is actually one of the easiest ones. 1 over n factorial, x to the power of n. So we derived the Mclaren series for cosine x and sine x and e to the x. And we saw that cosine x was sums and differences of the even powers of x, while sine x was the alternating series of the odd powers of x. But then when we did e to the x was its own derivative. And so every single value of e to the 0 was 1. So notice that every coefficient was going to be accounted for. So we had every single term in the polynomial, linear, quadratic, cubic, quartic, and so on. Now, when we added cosine x plus sine x, it looked like we kind of got close to what e to the x was. But it turned out that the main difference that we saw was that everything was the same except for these positive signs became negative, that positive sign became negative. And so it looks like some of the signs were the same, right? Some of the signs were equal. But other signs didn't quite fit the way they were supposed to. And what we left off yesterday with was the fact that when I take I and raise to different powers, we end up getting a very similar pattern that starts occurring. We should realize that if I take I and raise to the power of 0, I to the 0 is just 1. I to the first power is obviously just I. But what about I squared? How do I calculate I squared? What is I?
I is the squared root of -1. So I squared would be -1.
Exactly. If I square the square root of -1, then that becomes I squared. But then why is it that I cubed is the same as -I? Why do you think I cubed is -I?
Because it's -1 times I. Because it's
Yeah,
I
'cause
squared times I to the first.
Yeah, because I to the first times I squared is I cubed, but I know that that's -1 times I, which is just -I. And then when I go to I to the fourth is I squared times I squared, which takes me right back to 1 again. So this consistent pattern of powers of I is very similar to the sense that I see this alternating signs of positive, positive, negative, negative. So maybe there's a way for me to include the I values in addition to what we ended up seeing with the values that we have here in order to get those alternating signs to occur. All right. So what if we were to look at this in terms of instead of e to the x, let's take a look at what would happen if I were to look at the e to the power of ix. Wouldn't that mean that each of these x's would now just have an I included? And if there was an I included, now notice that each of those i's is going to be raised to different powers. And by raising I to different powers, all that's doing is alternating between positive and negative, and some of them become imaginary. Okay, so let's go ahead and work through that then. So e to the ix is 1 plus ix plus I squared over 2 x squared plus I cubed over 3 x cubed plus I to the fourth over, oh, these are factorials. 2 factorial, 3 factorial, 4 factorial, x to the fourth. I'm going to keep going all the way out to 7 if I can here. So we have I to the fifth over 5 factorial times x to the fifth, I to the sixth over 6 factorial plus plus x times x to the sixth. And finally, I to the seventh over 7 factorial times x to the seventh. And this continues on forever, okay? But you should recognize that anytime I've got an odd power of I, notice that it simplifies to be an imaginary number. Anytime I have an even power of I, it simplifies to become a real number. So with that said, that must mean that each of these values, when I start to simplify, are going to become 1 plus ix Let's do about 1. And then we'll go to plus ix. Now I'm doing these in different colors because of the fact that alternating values are going to be real numbers or imaginary numbers. So I squared is negative 1. Okay. So this simply becomes minus 1 over 2 factorial, or just 1 over 2 x squared. But then notice I cubed is negative I. So that next term becomes negative I over 3 factorial, which is over 6. But I'm going to rewrite this a little bit different, and I'm going to write this as I times 1/6 x cubed. Then let's go to the next one, I to the 4th. Well, I to the 4th is 1. So that means that I'm going to be adding 1 over 24, x to the 4th. But then over here, notice that I to the 5th just started over, right? I to the 4th is right here. I to the 5th is the same as I. So that must mean that I'm left with plus I times 1 over 5 factorial, which is 1 over 120. X to the 5th. But then we got I to the 6th. I to the 6th is the same as negative 1. So I to the 6th is just going to be minus 1/6, or 1 over 720 rather. X to the 6th. And finally over here for this last one, notice that I get plus, or rather I to the 7th is negative I, so I get minus I times 1 over 5040 x to the 7th. And this continues, right, as well. And so what I'd like you to now focus on are the pink values, or the pink terms, and the blue terms. What do you notice about the blue terms? If I were to just clump all of these blue terms together, well, let's see what happens. It looks like we've got e to the ix is equal to, so let's clump all the blue terms together. That gives us 1 minus 1/2 x squared plus 1/24 x to the 4th minus 1 over 720 x to the 6th. And then we get plus, and you should realize that the pink terms all have an I, so why don't we just factor out an I from all of those? And now write the pink terms. The pink terms are going to be x x minus 1/6 x to the 3rd plus 1/20 x to the 5th minus 1 over 5040 x to the 7th. And so what you should recognize at this point is if you take a look at the blue terms, that's exactly the same as cosine x. All of this right here is cosine x. And if you take a look at all of this over here, all of that, sines and everything, is sine of x. And it looks like if I add together I times sine of x, that would equal e to the power of ix. And what we have just done here, which seems kind of crazy, is that we have created what we refer to as Euler's formula. Euler's formula says that e to the power of ix is equal to cosine of x plus I times sine of x. And you might remember from trigonometry that this was actually exactly what we were able to do. Cosine x plus I sine x was how we were able to draw on a imaginary plane. So if I were to draw this, then essentially what this is saying is that x is representing an angle, right? So if I were to, for instance, if I were to draw this on a graph, remember that x represents an angle. So Euler's formula is showing us the relationship between trigonometry and exponentials. But not only that, it shows a really cool relationship about the imaginary plane as well. So if I were to draw, let's see right here. Okay, then this is the real and imaginary axis. All right, so if we were to call this the real axis and this the imaginary axis, then you might remember that when we were dealing with complex numbers back in trigonometry, we would be given some sort of angle, okay? Let's just say that that angle was, I don't know, right here. Well, that in this case is an angle theta, which in this case means that if this is theta and this is theta, then this thing up here is also theta. So we actually have this formula that says that e to the power of I times some angle is equal to cosine of that angle plus I times sine of that angle. So we're using power series, or we used power series to show this relationship. And so from trigonometry, we remember that this value out here on the unit circle is going to be cosine of theta and sine theta. Okay, but it's not cosine theta plus sine theta in this case, because what we should recognize is when we are on the unit circle, this right here is 1 unit away. This back here is obviously -1 units away. But if we look at this location up here, this is no longer 1, this is actually I. And this down here is -I. So this is giving us a structure of being able to draw complex numbers, so that we now recognize that this point out here is no longer just cosine theta sine theta, it's cosine theta and I sine theta. Which is pretty cool, because what that demonstrates is that if I were to add together like vectors, this vector, which is cosine theta, plus this vector, which is I sine theta. All right, if this is the vector cosine theta, and that's the vector I sine theta, then that means that the resultant vector, if you've taken physics, is going to be the sum of those two. But we just learned that the sum of those two vectors is e to the I theta, which means that that diagonal, or that hypotenuse, is actually e to the I theta. Which is kind of interesting already, that we're already starting to see that there's this formula here, which I keep referring to Euler's formula. Okay. Which is showing us the relationship between exponentials and trigonometric functions, so cosine, sine, and exponentials. But not only that, what happens when we're taking I times an angle? That seems weird already, right? Like when I take I times an angle, What does that even mean to multiply an angle by an imaginary number, let alone to raise e to that power? Secondly, e is kind of weird, right? E is a pretty cool problem here, or a cool number that we've given it the name e for exponential, but it's got the value of 2.718. You remember that? So e is approximately equal to 2.718. We're going to prove y in a second here as well. But one thing that I wanted to focus on is that if I were to take any angle, this angle right here looks like about pi over 4. So it looks to me like if I take cosine of pi over 4 plus I times sine of pi over 4, that would give me the same value as e to the power of I times pi over 4. What I would like to focus on is this angle right back here. Let's take this angle to be theta equals pi. Well, if theta is equal to pi, wouldn't that mean that we would plug in pi everywhere we see theta? So that would give me something like e to the I times pi is equal to cosine of pi plus I times sine of pi. But notice, if that's the case, then what that's really saying is, what is this distance right here? Because that's what e to the I pi stands for. So if that's what e to the I pi stands for, is that distance right there, then that distance is just -1, which makes sense because sine of pi is equal to 0, and cosine of pi is -1. Which gives me that e to the power of I times pi is equal to -1. And we can see geometrically why that's true. But that's not all. Let's look at what the significance of this is. What that's saying is, if I add 1 to the other pi side, I get that e to the power of I times pi is +1 is equal to 0. E to the power of I times pi plus 1 is equal to 0. And I don't know if you see what the significance of this is, but this is crazy. Because this one simple formula relates 5 of the most influential numbers ever discovered in history. 1, without 1, there's no counting. 0, the absence, 0 didn't show up in our number system until the Chinese, Mayans really were the first hundreds of years ago. E and pi, both transcendental, irrational numbers that have a significance. I being an imaginary number. Every one of these numbers, because of Mclaren series, has now shown up in one simple formula. I don't have any tattoos, but when I get a tattoo, this is what it's going to be right here. It's pretty amazing. I mean, this is just an absolutely insane relationship that we could see simply because of the fact. And if we go back again, this is by the way not on the test. This was just a really cool consequence of the Mclaren series. But if I end up looking at what the expansions for cosine x and sine x are, and we realized that they were similar to e to the x. And if we just multiplied, or if we just plugged in ix instead of x to the e function, we ended up getting that alternating pattern where this imaginary number showed up. And so we said, well, that's cool, but what does that mean? So we showed geometrically what it means. But then we said, what if we force that x value, that angle, to be pi? Sine of pi is 0, and it canceled out, which ended up showing me that even though that black Euler's formula right there is the standard relationship between e, cosine, and sine, the most beautiful part of the formula is that e to the I pi plus 1 is equal to 0. let that sink in for a minute because that's pretty freaking awesome.